Okay, I think we can get started. Thanks everyone for coming. So today to Colloquium, we are happy to have Dr. Yuan Tian, who is an assistant professor in the School of Computing at Queen's University, where she leads the RISE Research Lab, which develops reliable and intelligent support for software development. And prior to joining Queen's, Dr. Tian was a data scientist at the Living Analytics Research Center in Singapore. So Dr. Tian, please take it away.
Okay, thank you, Curtis. So good morning, everyone. I'm Yuan Tian, and I'm very honored to be invited. Unfortunately, I cannot join you physically in the campus. So today, I'm very happy to share some of our recent work on AI-powered software project management. And hopefully, at the end of this talk, you will get a brief idea about what are the research problems and opportunities in optimizing software project management, and inspire you to create more AI-powered tracking tools for improving software project management. So I'm currently leading a research lab called RISE that was already mentioned before. So the work that I will be presenting today are mainly conducted by my students within the research lab. And we actually have a very diverse lab with various cultural backgrounds. At this moment, we have 3 PhD students, 3 master students, and several undergraduate research assistants. They work on both AI-driven software development and software management. So for development, our current research focus is trying to build a large language model that can support automated code refinement, code transformation, and code generation. And for software project management, which is more relevant to today's topic, we're focusing on automatic technical debt management, pull request, or you can say code change management, bug and vulnerabilities management. Our research is mainly funded by METAX, Queen's, and Ernst. And recently, we also collaborate with psychology researchers to explore multidisciplinary researchers opportunities. For example, how can we apply some of the social theories in analyzing software project and management process? So if you are interested in any of these research topics mentioned here, feel free to reach out. We're very active looking for research collaboration and students. For today's work, I would like to start with a small quiz question to set up our common understanding ground for software project management. So the question is, which of the following tasks belongs to software project management? Select all that applies. So the options are interacting with clients, managing and tracking development tasks, fostering collaboration within the development team, ensuring software product quality, design software architecture, and write high-quality code. So 1 more minute. You can take a look at these options and think for a while. So the answer is that besides the last 2 options, the rest are actually considered as a common software project management task. The last 2 options, I would say they are more focusing on the engineering dimension, which deals with how to build a better software system. For instance, how can we design a better software architecture? How can we write high-quality test code? And how can we write high-quality source code? So software project management is a discipline that involves planning, organizing, and overseeing the development process of software to ensure that the projects are meeting their goals. So what do you mean by meeting the goals? For instance, whether the projects are completed on time within the scope defined by the customers and under budget. So to motivate our study and underscore the importance of software project managers, let's get back to 2004. So there was one researcher called Capers-Jones. He is actually an American specialist in software cost estimation. He conducted an empirical study analyzing 250 large software projects spanning from 1995 to 2004. So they define large software as projects with more than 10K functions. So in the end, they identify 6 factors that tell the difference between success and failure software projects. So they find that the success projects usually have effective project planning, project measurement, project cost estimation, milestone tracking, change management, and quality control. So on the other hand, the failure projects usually are being inadequate in doing all these tasks. And in the paper, he made a very strong conclusion in the end, saying that the reasons for software project success and the failure are actually associated with project management rather than the technical personnel. I think at that point, it's kind of surprising pattern because people usually think that in order to build a complex software system, we should more focusing on how to write a code, how to design better architecture. So in fact, I think the importance of project management does not only exist in software system. In other different organizations and in other industry domains, project management is also very important. It's kind of like the train engine that moves the organization forward to reach its goal. So that's why in the beginning of this presentation, you kind of see this logo or this icon, right? It's just trying to demonstrate that project management is the one that's trying to track you along from the beginning to the end and assuring that you're meeting the final project goals. And in the rest of today's talk, I would like to start by introducing a little bit of the background of modern software project management. Because as we already noticed, the previous study that we mentioned is already conducted 20 years ago. So things may change since then. And at the same time, understanding the evolution of software project management will also help us to understand why AI technology, or in most of the case, data-driven approaches play an important role in this big picture. And what are the existing challenges that exist or newly raised because we're using AI technologies. Then I will dive deeper into some of our recent work, especially focusing on two types of software asset management. One is pull request or code change, and the other is technical debt. But actually in the past, we also done a lot of work related to bug report management, but we won't mention that in today's talk. If you're interested, you can also check our publications. At the end of this talk, I also want to mention some of my vision about future work and some ongoing work related to large language models. So one of the most transactive approach to software project management after 2000, around that period, for modern complex software systems, I think is probably agile development. So before agile, in the traditional software project management, everything is planned upfront and executed step by step. So for example, people will start by conduct requirement analysis, talking with the clients, and then they move on to the next stage, which is architecture design, implement architecture, testing, deployment, and maintainers. So it's kind of a sequence. And on the other hand, agile development is more kind of flexible and iterative approach. So that's why we're seeing this circle here. It's iterative that every time they gradually improve over the previous version. And also start from planning until you finally deploy that to the customer. So the core of agile is provided in something called Manifesto for Agile Software Development, which was introduced in 2001. It defines several fundamental principles for better ways for developing software. It is actually a work of 17 software developers, practitioners, who have observed the increasing need for an alternative approach to documentation-heavy and the current heavy software development process. But in fact, agile is a very basic concept, or you can say it's a principles. And you need other frameworks or other ways to implement that. So nowadays, in most of the modern software projects, one way to implement agile is called Scrum. So in the Scrum, the work is actually organized into time-boxed sprints. And usually one sprint lasts 2 or 4 weeks. And each of the sprint will begin with something called sprint planning. So it is a meeting where the team members sit together and determines what are the things they want to accomplish within one sprint. And they also have a daily scrum. It's basically a daily meeting that able to track through all the states of the task. And at the end of the sprint, there are also two other key meetings occur. One is called sprint review. So this is where the teams demonstrate what are the things has been accomplished, and they want to gather feedback from the users to improve in the next iteration. And they also have another meeting called sprint retro. So it's kind of reflecting on what they went well and what didn't, and how they can improve it in the next sprint. So that is the basic idea of how Sprint can use to implement Agile. And the other dimension or things has been significantly changed is the availability of the tools and platforms can support the implementation of those Agile and Scrum process. For instance, we have a specific system such as Bugzilla and Jira. They allows developers and users to submit bug reports where the reporters need to specify where are the bugs occur and how to reproduce those bugs. And then developers can come and pick up those bugs and resolve them once they finish fixing the bug. And there are also other platforms such as the code review platform called Garrick. So it was used to tracking the process, how a code change was reviewed by one people or multiple people and modified until it is being merged into the code base. And if you say that I'm not familiar with any of the tool that you mentioned, you probably heard of or you probably used the GitHub before, right? So GitHub also have an issue tracking system and a pull request tracking system where they have the whole process and recording how an issue was raised and how the issue was resolved, how the code change was proposed, reviewed until it was merged into the code base. So that is an example of the tools are nowadays available to support better project management. And of course, there are always more advanced tools such as Jira. They also provide something called a Scrum boards, where you can see that in different meetings, people can decide and linking those bugs and code changes and decide what are the things they need to do, what are the things in progress, in review, and what other things can be marked as done. So how do the software project management change because we're having those tools? So one of the things that we notice is the increasing number of research papers that trying to use machine learning technologies for improving software project management. So Scopus is actually a data set that contains titles and abstracts of many peer-reviewed journals covering multiple disciplines, including software engineering. So here I just do a simple search or a search query that using keywords software project management and machine learning to search for any of the papers containing those two keywords in their abstract and titles. So we can see from 1919, the number of papers talking about these two concepts dramatically increased after 2014, I would say, or 2017. And last year, there are 124 papers mentioned these two keywords in the title or abstract of the paper, showing a strong interest of using machine learning technology in this field. And why this is possible? Because as we already mentioned, we have so many different tools and platforms where we can save and collect the data related to the software management process. And before those tools exist, we have no way to track what happens, right? It's mostly kind of in-person communications. So now if we have the data collected from those different platforms, then we have a way to apply data-driven approach to see what are the bottlenecks in those processes, what we can improve by analyzing the data. And that is so-called AI-powered software project management. So then probably you will say that it seems like we don't have any problems, right? We already have a very nice tool that can support this very nice modern agile development principles. Well, the thing is that unfortunately, we still have a lot of challenging faced with those tools. And even if we are following agile development, it's not guaranteed that your projects will always success, meeting the goals in the end. So what happens? So in this year, Mining Software Repository Conference, there was one paper, and actually I attended this talk. So I listened to the presentation. It's actually a paper discussing about agile planning in practice. And the authors are from Atlassian. It's the company behind Jira. So basically, they're the experts building the issue and project tracking software just now we mentioned. So they conduct a comprehensive survey with 50 companies using their tool, which is Jira, for agile planning. And they find that there are top 3 challenges faced by those companies. So for example, the first one is that it is a tedious and time-consuming task for the team to determine which issues they need to prioritize, means that which issue should be dealing with first, and which of them could fit the team's capability. So that is more about whether they can really fix it or not. It's very hard to determine this list. And the second thing is that they're enforcing bottlenecks. So for example, they potentially were suddenly receiving too many requests for code review from other teams or team members, or there will be unexpected back and forth code reviews, or even there's a lack of computing resource for code deployment. And which is even more worse is that there's a lack of actionable insight that they can gather from the whole process to mitigate those uncertainties. So they believe that they cannot handle that by themselves, just through the manual discussion and communication happening in the project. So when I heard in the end, they mentioned that to mitigate this challenging, they kind of motivate future research work that should focus on proposing a solution that can automatically identifying, classifying, and prioritizing issues. And I'm actually feel a little bit sad. Why I'm saying so? So it's very interesting that back in 2012, I had one paper that is exactly talking about the same thing. So I said that, so this is a 2012 paper. And this paper actually also won the most influential paper award last year at the Senior. It's a very important conference in software engineering domain. So in that paper, 10 years ago, we proposed an information retrieval-based approach that can help us to determine the ranking of the bug reports to specify their severity levels based on their impact on the user side. It is a data-driven approach. But now, after 10 years, they're still talking that this is a persistent challenging, means that there's a limited impact of our work in practice. So the practitioners are not really using or even aware of the AI solutions that we're building for the challenges that they're facing. So what happens here? Well, one of the reasons is that if you read a paper that they're trying to survey practitioners about their opinions regarding automated bug report management technologies. And they find that sometimes the inaccurate prediction in practice when the tool was used will lead to more time that developers will spend on doing that task. So for example, one of the survey response saying that the bugs from different domains have very different characteristics. Sometimes an inaccurate prediction would mislead us and take us more time to fix the bug. So of course, they are very unhappy about the actual time introduced by the AI solutions. And this is actually also true because if you're checking what happens in Visual Studio Code, so this is a repository offered by Microsoft on GitHub. They have a board called Visual Studio Code Triage board. So this is a board that have a lot of automated tasks, for example, checking the quality of the bug report before determining who should be the one picking those issues to fix. So this reporter actually submits one issue related to a VS Code version 1.71. So this is the description about the issue. And the bot comes and comments saying that, oh, thank you for the issue. It seems like maybe it is because you are using an old version of VS Code. You should use the new version, which is 1.71.0. So you should note that 1.71.0 is actually the same version that this reporter has mentioned in the description of the issue, right? But still, the bot failed because probably they're very strict on checking all the digits to describe the stable version mentioned in the issue description. So of course, the reporter is quite angry and saying that, look again, that's the version I'm actually using, okay? So because of those mistakes that people encounter when they're dealing with the automation solutions such as the bot, they kind of lose their interest or they feel disappointed in those AI solutions, which probably prevent them adopting those tools in the future. So definitely we need to work harder to improve the robustness of those tools, such as the ones that helping with the triage problem. And the other problem, which is more potentially harder to solve, is something called algorithm aversion. So for example, one of the response saying that different people will use different ways to describe a bug, how could the tool understand that they're actually referring to the same bug? So if you have some background in machine learning or NLP, you probably know that nowadays there are many different ways, such as word-to-vec or BERT models, can help us identify the semantic meaning of two different ways to describe the same thing. And actually, experiments have also been conducted that this is possible in the context of software engineering. So this is possible, but developers don't believe so. And there are many reasons contribute to this behavior. They're always thinking that, oh, machine learning solution is not better than a human judgment. So it could be related to the design, the accuracy, the explainability of the algorithms. It could also be related to the personality and how familiar are the person with those technologies. So if a person have used machine learning or AI solutions before, maybe they were more easier to trust those tools. So there are many different factors who lead to this result. But in any way, what we're proposing is that we still can do something here. For example, we can improve the tracking to make things more transparent. And we analyze the importance of those factors and present that to the developers. So in the first case, I want to mention two sample research that we have done for tracking what happens in the pull request. One is related to the time tracking, and the other is related to the reaction tracking. So a little background, pull-based development becomes a very common stand nowadays. And leveraging pull requests, contributors can independently modify the project artifacts proposing their code changes. So what they will do is that they will create a different branch, a new branch, and they will try to create pull requests. And this pull request will specify what are the proposed code change they want to merge into the code base. And of course, this code change cannot be directly merged into the main branch. They need to go through a critical code review process. So there will be some other people, reviewers, come and say that, oh, is there anything wrong with your proposed code change? Or do we really need this in our system? And in the end, either they will make a decision saying that, oh, we will accept this code change, or we will reject it. So if the pull request was accepted, that means in the end, it will be merged into the main branch. So one thing we want to kind of highlighting here is that what exactly is the time that people spend from creating a pull request till the decision was made, or until it was merged into the main branch, whether it is by minutes, by hours, by days. Because without analyzing these times, you're having no idea of a very important industry metrics to show the success and the schedule of the projects. So the time spent on doing the review on the pull request from its beginning to the end is a very important metric. So in the literature, what happens is that people find there could be many delays happening in any of the stage of this life cycle. So for example, some people will start saying that, can someone help to look at this pull request? So I want to ask for some code reviewers. And then the code reviewers may come and take a look at this pull request and say that, oh, maybe there's something wrong. You should improve the quality of your pull request. You should further clarify the content. And then the reporter will say that, oh, I have fixed these issues. Can you help me to verify again? So this iteration of the code review may continue forever. And so sometimes the pull request can be very long time. In the literature, there are several works that are trying to understand why there are so many times spent on this process, or what are the difference between those pull requests that having a much longer lifetime compared to the others. And what are some of the waiting time, which is the time that can be saved during this process. So what I want to mention is one of our recent work. We are trying to look at the very first step happens in this life cycle, which is the time when the pull request was created until the first response was arrived. So we call it first response time. And we are also building a tool that can helping people to track what is this first response time in their project. So if you have a GitHub project, you can apply our tool and you will get different statistics about what happens in your project. So one of the things we find is that if we separate the lifespan of a pull request into two parts, one is the first time response time, and the other is what happens after first response. Then we find that there's many kind of pull requests there in this box. So this box means that after first response, it just takes 1 day to resolve the issue. Okay, so it's actually not a very hard pull request to review, but it took more than 1 month for people to pick it up because that means the first response arrived very late. So what happens then? So by looking at this result, you may wonder, oh, maybe there's some problem happening when people are picking up the problem, right? Because that's the time determined for time to first response. So what we then do is take a look at those pull requests that belong to that category. So the first thing we noticed that in many of the pull requests, they got their first response very quickly, but actually it is because that they're using a bot. So there's a bot that automatically responds. So because you are having those bots, so definitely they're not kind of doing any task, right? They were automatically generating those responses. For example, there will be some bot that trying to ask people sign agreement in terms of contribution. So this is one kind of noise we should kind of consider when you're performing the data analysis. And the other things we find is that if you're comparing the time to the first response and the time to the first response by human, because we know that the first response can be made by human or the bot. So we find that most of the time, the first time for the human is much longer than the bot, which is making sense, right? Because for humans, it takes a while for them to review the pull request and making the decisions. So some of the studies actually can be explained by how many bots are involved in responding the first response. So if more bots are involved, that means you should exclude those responses generated by bots in order to understand what happens in the human process, because that represents the real software management process you want to track. And the other things we want to mention is that what is the relationship between this time to first response and the actual lifetime of the pull request? Because previous studies have shown that this first response time is very important as a good indicator for the whole lifespan of the pull request. But now if we say that there's a bot playing a role, then we should differentiate the first response made by human and made by bot. So we collect different features trying to model how different factors, including the first response time to the lifespan of the pull request. So these are the 20 plus features we have collected. And in the end, we find that indeed, if you're looking at a time for the bot's first response, it cannot explain anything related to the pull request lifetime. And if you're looking at the first human response, and that explains roughly 65% of the variance in the pull request lifetime. So still, the first human response time is a good indicator for how long will this pull request last in the final, right? In terms of calculating their lifetime. And the other thing is that we can also using the same model to do a prediction. So we can build a regression model and perform statistical analysis to see what are the significant difference between those have a shorter human response in the first round. And by looking at those features, we can think that in the future, those projects could potentially do something to improve their next iteration. So that is another example how this analysis can contribute to better software project management. And the final things we find very interesting is that the first response time from the human actually also have an influence on whether the newcomers will stay within the open source project. So that means probably when the newcomers find out that the developers, the contributors are very active in terms of responding their contribution, they will be more willing to stay within the community because that's indicating that this is a very welcoming communities. And this first response time, it seems doesn't affect to the existing contributors because they probably already have a good reason to stay within the project. The second task that we have done is related to the GitHub reaction. So I'm not sure whether you have noticed this function provided by GitHub. So when you are submitting a pull request, this is a description of the pull request. You can actually click this emoji and you have different types of emoji that you can select as the reaction to this pull request. So that is what we call GitHub reaction in pull request. Why this is important? Because you can kind of consider this as a new form of feedback. And it's kind of feedback towards the code change because pull requests represent a code change. Since it's related to both feedback and code change, which is actually the core part of agile software development, we think that this is very interesting for us to understand and to track these statistics. So there was one Towson paper related to this topic. There are several findings that we kind of find from the studies. The first one is that we find the reaction actually show different things than the comments within the pull request. So what does that mean? So the first thing we do is that we're trying to check how many of the reactors, those are giving reactions, are actually leave a comments in the same pull request. So we see that most of them do not leave. So the conclusion is that most of the reactors do not leave a comments in pull request. And on the other hand, we can also check how many of the commenters give the reactions in the same pull request. And the result is also the same. Many of them do not leave a reaction. So what does that mean? So that means that the people who are leaving the reaction is a different set of people than those who are making the comments. The reactions are actually carrying out new information, new feedback from kind of audience rather than the comments. So instead of, for example, analyzing the sentiment, the opinions happens in pull request comments, it will be also interesting to look at what happens in those reactions. So what happens there? So the second questions we want to ask is who are actually participating in this behavior, who are giving those reactions, and what they are reactive for. So to answer these questions, we need to create new algorithms to track the statistic because GitHub does not provide this information to us directly. So when you're looking at a pull request and the reactions, what you can do is that you can click this reaction emotion, and it will tell you that what are the people who are react using what kind of emoji. So they actually have a list of people who are giving these reactions. So by using those usernames, we're able to track who are giving the reactions on this pull request. At the same time, we can also check what happens in the discussion, which is the comment. So when we're checking the comments, we can see whether the people who are giving the comments is also in the list who are giving different reactions. In that way, we have a way without interviewing the people to see that why they're giving this emotion, because they're also making a comment, okay? So that is the methodology we use to understand this, to answer this question. So what we find is that the outsiders, so outsider means that they are not making any contribution in the code base. They are likely to be the user or the target, the other developers who rely on this product, but they are not contributing to the product. So those people are actually very active in giving those reactions. So that's why we say that maybe we can consider reactions as one way to capture the user feedbacks on what you have to do on the changes, collecting the feedback. And by manually looking at the comments leaving by the same people who are left the reactions, it could be outsider, it could be the co-contributors. What we find is that the contributors' reactions are more related to the code part of the feature, while the outsiders' reaction, they are more related to user experience, which is kind of under our impression, right? Because we say that if they're the users, why they're making the reaction? Because they feel that this new feature is useful for them or is not necessary for them. They're more caring about the user experience. And if you're the contributor, the code contributor, what you care is the quality of the code contribution. So that also means that when you're looking at these numbers, when we say that you're designing a tool to track those statistics, you cannot simply just take a look at them. You should see who are doing this behavior, because outsiders and code contributors, they represent different opinions. They should be separately. They shouldn't be aggregated together by looking at the numbers. So the second case I want to give is related to technical debt. And there are two scenarios we are targeting. One is called tracing, and the other is called duplicate SADD detection. So SADD is actually means self-admitted technical debt. It's actually within the code command. Sometimes we will write such as to do, this method is too complex, we will fix it later. So it's kind of indicating that the current state of the code is not optimal or is suboptimal, and we want to do something to improve it in the future. It's kind of indicating of technical debt. And the research area related to SADD, the most active one is called SATD detection. Means that given the software, we want to track where are those self-admitted technical debt, and we want to learn from them. For example, how long does it take for us to close those technical debt? And a trivial way to do detection is using the keywords, for example, to detect whether those keywords to do, fix me, unfinished appearing in the code command. However, at the same time, the project itself is evolving. That means things changing in the way, right? So when looking at the software technical debt, we are thinking that there's also life cycle for SADD. They could be created, they could be modified, and in the end, they could be deleted. So if you're going to track those statistics, you should know when they get updated and when they got removed. But if you're using the existing technique, what happens is that they will manage to take a look at when this code command containing the keywords was removed or added. It was added, then we say a new technical debt was created. And if it was deleted, then we say that, this technical debt was deleted. So that is what we can do by using existing detection tools. And what we're thinking is that if we want to track the lifespan, that means we want to identify the place where those SADD get replaced or get updated. So what we do is we're collecting the information related to the commits, and we're trying to identify where they occur. So that is the first step. And then we need to deal with the false positive in terms of detection and to differentiate that from modification. So what does that mean? So I have one example here. For example, in this case, we're introducing a SADD in this line, in this commit. And in another commit, we actually modify this line by adding something. So it's a modification. But previously, because we're only able to track where this line got removed, we will say that, this SADD was deleted. And another SADD was created. And this one is the new one. So in the end, what we want to do is we want to say that, this is a false positive. It shouldn't be an actual deleted. It shouldn't be actual create new, but it's actually a modification upon the existing SADD. So that is what we want to do. I think due to the time limit, I will just quickly go over the algorithms. So what we do is we're trying to decompose the task by focusing on the pairwise mapping between the commits involved in different SADDs. So for example, we want to see that there's a potential that some SADD are actually referring to the same one because they just got replaced rather than removed. So we do a kind of pairwise calculation based on the content of the SADD, the contextual information related to SADD to determine how similar or what is the likelihood that they're mapping to the same SADD. And we're using some threshold to determine, say that, SADD1 is actually referring to the same SADD as the ones that appearing in another commit. So once we have those pairs, then we are able to connect everything together as a whole. So for example, we're able to identify that commit 3 is actually mapping with SADD7 in another commit. So if we have the pairwise commit, we can actually link them together to tell the whole life cycle of one commit because we know what is the each state along within each of the commit. So then we say that SADD1 was created in one commit and was updated in commit 2 and 3, and finally was deleted in 5. So that's where we get the whole life cycle in terms of tracking where are those SADDs. So I will just skip the details. You can look at our papers. So one of the contributions is that we're introducing a weighting system because there are many different contexts can contribute the way that you're calculating the pairwise similarity. So we're using a learning algorithms based on some label data to come up with the best weight distributed for different aspects. And of course, the result shows that the performance of our approach is better than the existing ones. So the final work is related to clone or duplicate management, which is also a very kind of focal point for software project management. For example, in terms of source code, we can have different copy of the same code everywhere in the system. And this will introduce the problem because sometimes you will forget, you only make the changes to one piece of the code clone while you forget about the other place where you use the same piece of code. And this also applies for the bug reports where you want to detect that these two bug reports are actually referring to the same problem, so you should resolve them together. So this is called duplicate management for bug report. And we're thinking that the same thing will happen in SADD management because you may have two or more SADD referring to the same problem, same technical depth. So in order to manage them, you need to group them together. But the question is like, how can we identify that one or multiple SADD should belong to the same group? So what we do is like, first, we should identify where those SADD comments occur, and we will filter them because some of them are actually automatic generate. And in the final stage, which is the most complex part, is that we need to calculate the similarity between this SADD while comparing with the other SADDs. So if you say that this SADD is somehow similar to one of existing SADD, then there's a chance that they should be grouped together to form a cluster. So what we do is like we're setting a threshold to say that if any of the similarity score for this SADD is larger than a value, then we will keep that as a candidate to form a group. Otherwise, it will be just isolated group. And once we have the scores, we can generate a matrix. While for each of the SADD, the similarity between this SADD and the other SADD actually becomes a feature vector, representing how similar is this SADD to the other options. So once we have this vector matrix, we can run a clustering algorithms. Well, the idea is that if those data points SADD belong to the same group, they should all similar with each other, and they're different from the rest of the SADDs. And it turns out that this algorithm works very well. And we find that surprisingly, in many of the popular projects, more than 50% of the SADDs are actually duplicate. And this is a huge problem because if you're not knowing this, you probably have a wrong estimation on what is the amount of technical depth exists in the software project. So you may like oversee the problems because you are not aware of the duplicates. So the final part I want to mention about the future work and ongoing work. So we all know that nowadays large language models such as the open source ones and the closed ones are extremely popular. So in terms of our context, we want to know whether these large language models can really help with software project management. So we have ongoing work that trying to use these models for detection and classification of SADD. And what we do is that we're actually using Flantify, which is also very famous and powerful large language model, but it's not following the GPT kind of architecture. So those generative models, because they are for generation, the design is not kind of for a classification problem. If we want to use them for classification, we need to do some modification. In the final layer, we need to connect with the classifier layers. And when we're doing the experiment, so this is just an initial result for some of the things we have already conducted, we find that compare with the ruler-based approach, such as the ones that only focusing on the keywords, this Flantify plus fine-tuning on a small set of data can get a much better F1 score, which shows the promising opportunities of applying those large language models for this task. And the other things, this is from another dimension, is that when we are looking at the projects, maybe the projects that involving AI technologies and LLMs, their looks very different from the other software engineering projects. And in actually, in some of the recent work, they also identify some of the conflicting between the AI project workflow with the traditional software project logic and the agile development principles. So that means maybe these two things are no longer work very well when you have an AI or machine learning product, because their pipeline looks very different and the people involved in developing those AI and machine learning products are also different. So how can you encounter those different or even conflict when you are using the traditional approach? You should propose the new solutions for those AI projects management. Okay, so I think by saying so, we will end the talk related to AI-supported software development. I think we have seen some of the potentials of using data and AI-driven approaches to improve the tracking, classification, duplicate management, time tracking for different type of software assets. And I will say that building easy to integrate and intelligent tracking tool is a promising start point, but there are much more things we can do. For example, we can make them robust and we can educate more on the usefulness of those tools. We can incorporating more powerful large language models. Last but not the least, another call for collaboration on topics we mentioned in the beginning of the talk. We are really looking for collaborations and students who are interested in those research topics. And if you have any question related to this topic or anything, you can connect me through this email showing on the slides. I think that's end my presentation. Thank you. I will be happy to take any questions.